to kind of go over some of this homework in some detail, if that's okay.
We'll do okay.
Thank you. Because really the homework assignment tonight, or that you had for today, had a lot of what's going to be on the quiz. I mean, if we look at what we said was going to be on the quiz, we had chart, global max min, and 44, and I apologize for not telling, I didn't intentionally not tell you, but I didn't think of it. The number 44 on the 2.7 was a calculator one. So at some point I would think you would have done the derivative, set it equal to 0, tried to solve it, and then figured out I can't solve this with a calculator, and then would have went to the calculator done. Okay? And so I want to talk about some of the specifics there about how how we got to use the calculators, to solve those and what that problem would look like. But basically it's the same kind of problem with the list of candidates or the number lines and all that. So that's a big part of the quiz. And so there were those problems on today's homework. There was this idea of differential equations. And two of the main three things I want you to do with differential equations were on today's homework. One is identify the kind of the type of differential equation is and be able to work with it. Like the one on the bank interest. I don't know if you recognize that on section 2.6, but that was type 2 on the differential equation. It was the PERC formula. It was the exponential that you were supposed to use there. And first time we've run into that, but some of you may not have noticed that, but that's what that is. So be able to use a differential equation, use the solution of a differential equation, which is the original function, and be able to answer questions. That's one thing. Another thing would be verify something's a solution. That was most of your homework on the differential equation, a lot of the T-chart, verify solution. And then the third thing I want you to do is this idea of an initial value problem. We're going to talk about that in a minute. Initial value problem, your book on your homework today will talk about IVP, solve the IVP. Well, solving IVP is the same as solving a differential equation. An IVP is just a differential equation where they give you an initial condition. Okay?
I need him.
Him.
Are you forgetting something?
No, I was going to be here halfway and only come in.
How would you get that one?
Okay.
Is that okay?
That's what I told Honeycutt, but I guess it's not sufficient.
I guess not. She was kind of out of breath. I mean, like,
Maybe I should.
we need you. Well, if you need to go check, I don't want you to get in trouble.
I might be back.
Okay. Go check. All right. So an initial value problem is like an initial condition where they tell you, like on the bank problem, they told you start with $2,000. Okay? That's an initial condition. Remember, we said when you do an antiderivative, like right here, when we do one of these where we do the antiderivative, we get a plus C, right? Well, there's an infinite number of solutions. On some of the homework it asks, how many solutions do you have? Well, what they meant there's an infinite number of solutions. But if they give you an initial condition, now there's only one solution. Because now you know what the C is. You can plug in the initial condition and get what the C is. So we'll do a few examples of that. So if you can do those things with differential equations, and that's pretty much what I want you to be able to do. And then, so there was the chart and the global max min. The only thing there wasn't really much of was the derivative, antiderivative formulas, although as you were working those problems, you had to do some derivatives and some antiderivatives, so you got practice on those. So really, if we can go through some of this stuff that the homework's about, that covers a lot of the things you need to be able to do on the test, okay? And I will hit in some stuff with differential equations. I guess one other thing about differential equations I want you to be able to do. So we'll talk about that a little bit in here today too. And then we have another homework assignment very similar with those kinds of problems, more practice. Tomorrow we can answer a few more questions, and then some more work time, hopefully some practice time, and ask questions there as well. Speaking of the videos, on the website, before I forget about it, I'm just going to go ahead and say now, on the website, carneycats.com, on our class site, of course I have the link that says class videos, and that's where, and in chapter 2, and that's all the different days videos. But I also have this new one I put on here. It says 2.4 to 2.7 review videos. Okay? And what I've got here, they're very exciting. They're me talking and working out. So what I did is I have a document camera, and I just have a piece of paper under the camera, and it's just a recording of me working out a problem and talking through it. So they're only like 5-10 minutes long at the most. Okay? So I've got one that's just a basic local max min with the number line. I've got one that's a global max min with a list of candidates. I've got one with inflection points that uses the trig. Okay, so it talks about second derivative, doing a number line. I've got one that I recorded in class a couple years ago when we just did about a 25-minute review of trig stuff. So if you want to watch that one. Solving a differential equation or an initial value problem. Okay, like I was talking about there with the initial condition. So I've got one of those. And then I've got a trig local max min without a calculator. So going through the number line and stuff. So if you can watch any of those, just, going through the steps, emphasizing what it looks like, what your work should look like, and so forth. Yes.
So the trig goes with anti-derivative.
Say that again.
Or the unit circle, like those kind of problems.
Right. Those would go with the unit circle. That kind of stuff would go with your max min kind of problem, where you have to do the derivative and set it equal to 0, because you end up with like sine x plus a half equals 0. So you subtract a half, you get sine x equals negative a half, and you have to know when sine equals negative a half. So you're stationary. So that would, the trig stuff would be in your in the max min chart. Okay. All right. So let's start with. Let's see. Let's start on the differential equation stuff. So, what would be 1? 6? Would that be worth looking at? Getting that one to match. 6. Something. Now, a few people came in this morning. We talked about number 6. They give you this differential equation. Now, I kind of meant to mention this. I just was hoping everybody realized it. They don't write it very well there. They wrote it like 1/2 y. Maybe I did talk about that. It looks like 1/2 y, but it's not. It's 1/2y. But it's like the one I did in class. Okay, so I was hoping you recognize that. All those ones down there. So if you wrote it 1/2 y, that would be a problem. Yeah. So if you did that, then that might be where you went wrong. But there is something else that's a little trickier to it. Now remember, they are saying is y equals square root, what is it, c minus x, a solution. So what we have, again, like we talked about yesterday, they have proposed that that is a solution. Just like yesterday, we proposed that x equals 6 was a solution to this. So what did we do? We took our proposed solution, plugged it in to see if it worked. Okay, in this case, we're going to take the proposed solution and plug it in over here and see if it works. So in place of the y here, I'm going to have square root c minus x. And over here, I need y prime. Where do I get that? I have to do the derivative of this one. Now, first, I'm going to rewrite it. And now I'm going to do the derivative of it. So I bring the 1/2 down in front, and then I've got c minus x to the, right? Everybody good with that? So I plug that over here. 1/2 c minus x. Are those the same? If I bring this down to the bottom, one's negative and one's not. So they're not the same. However, we did something wrong. Well, we didn't do anything wrong. We just didn't do enough. Whenever you multiply a number on the inside to the x, you have to kick it out. Whenever you multiply a number on the inside to the x, you have to kick it out when you do the derivative. There is a -1 multiplied times that x. We've got to kick out a -1 here. So there should have been a negative on a derivative, and so there is a match there. Okay? And everybody always misses that the first time. Okay? Hopefully from now on you won't. But when you multiply something times the x on the inside, we have to kick it out when we do the derivative. Okay, so it does match. It is a solution. And on today's homework, they're going to refer to this differential equation again, I think like on number 8 or number 11 or one of those. And so we've now shown that that's a solution, so we can now use that as the solution in those problems. Okay, and then go on. Okay, so that is the solution. That's called the general solution, meaning there's an infinite number of them because we don't know what C is. So every time C is something different, it would be a different solution. Right? But if they gave me an initial condition, this is this idea of initial value problem. if they would tell me that y of 0 was 2, for example, what would I do with that information? Put a 0 for x and a 2 for y. So I would have 2 equals square root c minus 0. Then what? Put a 0 for x, a 2 for y. Square both sides. Now, whenever we do initial value problems, people always want to stop here. It feels like you're done, right? This is what in algebra, when you got the c equals 4, you were usually done, right? We've got differential equation is the original function y. So we want the solution to this differential equation, which was this. Well, now we found c. We now have to take that 4 and plug it back in for the c. So the answer is y equals square root 4 minus x. Now, not on 6. I'm not talking about that. I'm talking about today's one. They'll say solve the initial value problem. So it's the same thing. So here's the solution, which we already knew. Now they give me this initial condition. So this is why I put this on the board. I'll just leave it up here. A differential equation plus an initial condition is called an initial value problem, an IVP. So people always kind of freak out when it says solve the IVP. What's that mean? What's that mean? It's just a differential equation, but instead of having a C in your answer, a plus C or whatever, you'll be able to put in that initial condition, find C, and then don't stop there, put the C back in, and then write out your solution, write out your y equal. Okay, another thing that came up in the other class that I had to really emphasize, so I'm going to just talk about it right now. When I say the solution to a differential equation is the original function, what I mean is it's y equals and then x's after that, or t's, whatever the input variable is. It won't have any y primes in it. It won't have any other y's in it. It'll just have y equals and then x's. Now, there could be a plus c in there too. But otherwise, it's just y equals with x's. Okay, that's how you tell the difference between your solution, which is an equation we're used to seeing, y equals something, as opposed to a differential equation. It's all messy. It's got primes in it, and y's, mixes of y's and y primes and x's and all kinds of stuff. So when we look here, see our solutions to a differential equations are equations we're used to working with. Y equals 3t plus c, y equals 3x squared minus 5x plus c, y equals a e to the kt, right? The differential equations are that, look like that, okay? So that's something, and the y is always the output variable then. So it might be p, or it might be f, or it might be something else, but it's your output variable that the prime is always on. Okay, so that was 6. What else on that 2.5 section? Anything else on that 2.5 section? 17, okay? 17, was that the one that said, yeah, here is our proposed solution, right? Solution question mark. And what's the differential equation? See, and people often ask me, where do I put the t? Where do I put the t-chart? I've got 2 equations there. Do I put the t-chart here? That's why I always write this proposed solution thing. Remember, like my algebra example, is x equals 6 the solution? I don't know. Let's plug x equals 6 in. We always plug the solution into the equation. So this is the proposed solution. This is what gets plugged in over here. So 3, I'm not going to put anything in for that. That's just going to come down. But for the y, I'm going to put x cubed. X, I'm not going to put anything in for that. But for the y prime is 3x squared. If y is x cubed, y prime's got to be 3x squared. So in place of y prime, I'm going to put 3x squared. So x times 3x squared is 3x cubed. This side is 3x cubed. Okay? So, I mean, yeah, that's it. I mean, is that the confusion sometimes? What do you put where? They give you like these 2 equations, like what do I, so, I mean, that's how I say it. I don't care if you use a t-chart, just somehow verify that that makes that work over there. But I just think this is the cleanest way to do it. All right, what else? What was 25? Oh, that's another one of those same ones. Proposed solution and the differential equation. Whoa, hey, hang on. Y double prime, well, I just wasn't ready. Y double prime minus equals, okay. So obviously nothing to do over there. So y double prime, well, y prime is 2x and y equals 2. So y double prime would be 2. 4x times y prime, which is 2x, plus 4 times y, which is x squared. Yeah, it's pretty easy to see already. 2 minus 8x squared plus 4x squared. 2 minus 4x squared does not equal 0. Not a solution. Not a solution. Okay. Now, somebody asked me this new, if most of them are going to be true, or the ones that they, I mean, when they give you one, can you assume it's going to be true? Well, obviously not there. But the directions there were a little different. They said decide whether this is a solution, right? When they say verify that this is a solution, probably the one I'm going to give you, because a lot of times what we want to do is we first verify that it is a solution, and then we go ahead and work with it. Give you an initial condition, plug it in, find some value. Yeah. Yeah. That should. You could rearrange them and then plug stuff in, and it still doesn't matter. Yeah, that's okay. Okay, what else? Seems to me this wasn't the one we did 37, right? 38. That's on the next section. That's 2.6.
38's on.
Okay, so let's go to section 2.6. Okay, and was this one that had the bank problem, 47? No, let's do that. Can we talk about that one? Because this one is about a differential equation. Okay, section 2.5 is differential equations, but then we get into section 2.6, which is exponentials and logs, and they're most useful, the best use, or one of the best use of what we're talking about is in differential equations. So that's why a lot of the examples involve that. We don't get any max-min problems because e to the x doesn't have any max-mins. It's always increasing, and ln x is always increasing, and so you don't get much of that. We get more of that in the trig section. Okay, so that's where we'll go with that. But so on 47, they tell you that you've got money in the bank. Now, hopefully by Monday, this will be an automatic for you. When you see this, okay, that's a differential equation. P is like the y now. That's the output variable. But hopefully, as soon as you see that, you will think of this right here, number 2. Y prime equals ky is the same as p prime equals 0.08p. And so right away, we know that this is an AE to the KT equation. Okay? So as soon as you see that, or as soon as you know it's money interest kind of a problem, that the first thing you do is write P equals AE, and then the K would be 0.08 T. That just needs to be automatic. That's recognition. You say, okay, that's that difference equation we've kind of memorized, so I do that. Now, also understand that we could have written this differential equation as P prime of T equals 0.08 P of T. We just use it's just messier when you put in the function notation there. So with differential equations, usually we don't write that. Okay, it's nice if they do because then you know T is the variable they wanted you to use. Okay, but so in this case, I could have put P of T here. Okay, usually we do when we write the solution because we kind of like having it in function notation. Now, what's the other thing they told you in that problem? You put in $2,000 right away at the beginning. Now, many of you know that that's the A value, okay? And I get that. But that's only because that's at time 0 that we have $2,000. So I really want you to think of it this way. I want you to think of this as an IVP. This is an initial value problem. What they did is they give you a differential equation here with an initial condition. That's what that looks like. And differential equation with an initial condition. Now, P is the output variable. That means the solution of this differential equation has P prime in it, should be P equals, and then only have input variable in there, like X or T in this case. Okay, so that's the solution. You'll see what I mean here when we look at the problems in a minute. So we go ahead and we put 0 in for T, and so we get 2,000 equals AE to the 0.08 times 0, right? That makes sense? I just put a 0 in for T. Now what's 0.08 times 0? 0. E to the 0 is 1. So sure enough, we get A equals 2,000. So now the equation, like I was saying on that example I did earlier, now that we found what A is, we're not done. We now take that and we put it back into the equation. So the equation is P equals 2,000 E to the 0.08 T. So that is my solution to this initial value problem. Now, but this is what we can work with. And I want you to understand this about differential equations. The power of differential equations is they simply, pretty simply, describe natural phenomena. In other words, this says the rate that your money grows is proportional to the amount you have. That's a pretty powerful statement and pretty simple statement. But what it doesn't do is help you find how much money you have at a certain time, because there's nowhere to plug in the time. So that's why you need the solution to the differential equation, because that's the one that lets you find specific values. So differential equations model physical situations really well, but they don't help you solve those situations very well. So when we have the solutions to them, then we can use that. So after 10 years, what do you do? To answer the question, how much money is there after 10 years? You put a 10 in for T. This would be a calculator problem. You put a 10 in for T and you just get it. Or what if it would have said, and here, who's John? Here's where you're going to be up here in a minute. Calculator. What if they would have said, how long until you have $5,000 in the bank? You'd set this, and since it's a calculator one, we would solve it. So go ahead and, so we would write that down. So if I said, how long till you have $5,000 in the bank, you would set up this equation. Be sure and write it on your paper. Any equation you solve in your calculator has to be written down first on your paper. Okay, so John's going to go to the calculator, and anybody else can if they want. And what happens? You get logged out? Try logging back in. Something happened. That happened to us this morning, too. That looks like you did. Okay, there it is. So notice he goes to menu, algebra, and everybody's got to make sure they can do this today, okay? So I mean, if solving on the calculator is easy, you have no problem with that. Fine. I am going to show you a couple of little new things with that today, though, so we want to make sure. And look at that. So we got solve 5,000 equals blah blah blah. Type it in 0.08. You want to use X here is fine. You can use T. I mean, whatever, doesn't matter. Okay, then he's got to put comma X, that's true, comma T, whatever you do. So what's that mean? That many years. 11.454, remember, always 3 decimal places or more. You can give more than 3, but you have to have 3. Now, on tomorrow, at the beginning of the period, I'm going to hand out those quizzes from the other day. And there was a couple problems where some people forgot to put like 3 decimal places. Anytime you give a decimal answer, make sure it's at least 3, you can have more. All right, so it'd be that many years. So we could use a calculator to help solve that. All right. So that's the differential equation stuff. I tell you what, let's go back here a minute. In your book, on page 122, 130, sorry, 130, in your book, page 130. In your book on page 130, the top of the page, read that those directions there in italics for problems 32, 33, 34, and 35. Okay? So we have this idea, they have this situation, position, velocity, acceleration, and they tell you this. So A is the same as what? Excuse me, V is the same as P prime, and A is the same as, well, V prime, but also P double prime, right? So it goes position, then derivative, that's velocity, derivative, that's acceleration, right? Okay, so now, so I was talking about difference equations, different things we want to be able to do. So we just talked about a problem where you use the idea of you know what the solution is, you plug values in, you can find values, okay, that kind of thing. We can verify solutions with the T-chart, we want to be able to do that. And now, but I also want you to be able to do this. I said that differential equations help you model, pretty simply, real-world situations. I want us to be able to write this. So, look at 32. 32 says, well, first of all, the last thing the direction said, write a first-order differential equation. Okay, so let's review that real quick. First order, what's that mean? Well, it's kind of like in algebra when you have a first-degree equation or a second-degree equation. What's a second-degree equation? What's that mean? Second-degree equation. This would be from algebra 1 or algebra 2. Square. Second-degree equation means it's a square. First degree means it's first power. Third degree means it's third power, right? It's a high power. Okay? A differential equation is kind of the same thing. A first-order differential equation means it has a y prime. A second-order differential equation means it has a y double prime, and so forth. Okay? So what they want, when they say write a first-order differential equation, what they're saying is write an equation that has a one derivative in it, just a y prime, not a y double prime. Okay, that's what that means. All right. Now, so on 32. So on 32, they say we have an object traveling at a constant, what is it, velocity or acceleration? Has a constant acceleration westward, so that would mean what? Westward. Negative. So it has a constant acceleration westward of -5. Well, wouldn't this be the equation that would say that right there? So I want you to be able to translate words into notation. But that's not good enough because they wanted it to be a first-order differential equation. So they want it to have a derivative in it. So instead of A, we should put what? V prime. So this would be the answer to number 32. That is a first-order differential equation. Remember, what's a differential equation? It's an equation that's got derivatives in it. If it's got an equal sign and it's got derivatives in it, it's a differential equation. So that is all you had to do for number 32. Okay? 33 says, what? Object travels eastward at a constant speed of 15. So they're saying the velocity is 15. But that's not a differential equation. So instead of velocity, we'll write P prime equals 15. That's a first order differential equation. All right, 34. Now I want you to be able to do this. 34 says because of friction, the acceleration is proportional to the velocity. The acceleration is proportional to the velocity. So that would be A equals, how do we write proportional to? Right? Everybody, there will be something on the quiz where you will have to do that. Okay? Whenever it says, we talked about this in one of the very first appendix problems that we did, and the story problems. If you have something that varies directly or proportionally to something else, there's some constant of variation that we have to put in there, so we just call it K. So if you have that sentence that this is proportional to this, we put K in there. So what did it say? The acceleration was proportional to the velocity. Okay, so but that's not good enough because we want a derivative in there. So what could we replace? We could replace the A with V prime, and that is good. That is what we want to do because we want there to be V prime and then also V. Now I would say this looks like our, this looks a lot like our interest one, doesn't it? y prime equals ky. But now, here's the other thing I want you to think about. What would the solution of this look like? Remember, the solution of a differential equation is the original function y. Now, that's if y is in the problem. Y is not in this problem. The solution of this would be what? V equals, and then something, something. Well, we know it'd be a e to kt, but it'd be something, something with x's in it, or t's, right? Remember I said that earlier? The solution to a differential equation is the original function, no derivative, the original function, and then like x's. So in this case, the original function is v. And it's the output variable because we can tell it's got v prime on it. So it'd be v equals with some x's. Okay, you just need to understand it. Now, that would be our answer because they wanted a first order differential equation. But wouldn't it have been okay to replace the a with p double prime? If they wanted the second order differential equation, right? I could replace the a with p double prime, but I would need to replace the v also there. See, because I don't want a problem that's got p double prime and then has v in it. Those are two different output variables. I don't want that. I want the same output variable in there, but v is the same as p prime. So I could have written it that way. That's the same thing. But now the difference here, and this is really key, the difference here is what's the solution to this going to look like? No, the original function. P equals, and then some stuff with x's in it. Okay, now understand this now. These two are the same. These two are saying the same thing. The difference is the solution to this would be v equals something. The solution to this would be p equals something. So which one you used would depend on whether you wanted to know velocity stuff or you wanted to know position stuff, right? Now, you're not going to have to make that decision on quiz. I'm not worried about that. But I do want you to understand that idea of the solution to a differential equation is the original function. So on the bottom one, the original function would be p. On the middle one there, the v prime, the original function would be v. Okay? All right. So that's kind of just an important concept. All right. And then they also said there that the proportionality constant is negative. The k would be negative. Why? Let's go to this one. Don't look at this one. Okay? It says because of friction. Well, if things moving, what does friction cause it to happen? Slow down, right? So if this thing's moving to the right, v would be what? No, Al, careful now. Because it's going to the right. That doesn't have anything to do with slowing down. Because it's going to the right, its velocity is what? Positive. Because it's going to the right, its velocity is positive, right? Going to the right, velocity is positive. Going to the left, velocity is negative, okay? So its velocity is positive. So the v here would be positive, right? What's v prime? As this is slowing down, what's that mean? Is its velocity increasing or decreasing? Decreasing. So if v is decreasing, right? Since it's slowing down, its velocity is decreasing. What's v prime? Negative. So since v prime's negative, and we know v is positive, what's k got to be? K's got to be negative. Okay? So you might have to do something like that. You might have to give some sort of an explanation of why k has to be positive or negative based on the chart. That's just the chart. Since the object's going to the right, its velocity is positive, and since its velocity is slowing down, since its velocity is decreasing, we know v prime's got to be negative. That's off the chart. That's why k is negative. Okay, let's do one more. Let's look at number 43. Everybody read 43. Just read number 43. All right. Now, on 43, it says to write a differential equation that describes this situation. You may have to do something with it. Okay? There's a situation. You don't have to do anything with it, but you have to write it. Okay? So I'm going to call the object coffee. Okay? So we've got a cup of coffee sitting here, like 180 degrees, right? Hot coffee sitting in this room that's about 70 degrees. Now, isn't this what it was saying there? T then would be the temp of the coffee, and S would be the temp of the room. Walk right in.
You know, I tried to
She tried to
do
be
people,
not.
interrupt me when I try to do
And the class was very good. They did. It was my fault. They
That's exactly
Just-
like what we're doing.
This is exact.
Yeah, we're doing temperature stuff right now.
In chemistry too.
Oh, is that all right? Well, good. We're doing a little interdisciplinary stuff here. All right. Get out of here.
I just want to see how distracted they.
All right. So okay, so let's read this, because really all we're doing is translating the words into notation. So what's it say? It says the temperature, or no, the rate of change of the temperature, right? Isn't that the first sentence says? So what would that be? The rate of change of the temperature. So like degrees per minute or whatever, right? So the rate of change of the temperature, T prime, is, so that's equals, then what's it say? No, it says proportional. So K, proportional to what? The difference of the temperature of the coffee and the surroundings. So parentheses. Right, now that's pretty easy. I mean, that's not that bad. I mean, that's not that hard to transcribe. Rate, we know, is the derivative. The rate of change of the temp of the coffee is proportional to, right, a K, the difference between those two. Now think about that. Proportional means as one gets bigger, the other gets bigger, or vice versa. So the difference, so if I got a 180 degree coffee in a 70 degree room, there's a pretty big gap between those two temperatures. So if this number is big, that means T prime's got to be big. The rate would be faster. Wouldn't it cool? Wouldn't the temperature be changing faster if the coffee's 180 and the room is 70 than if the coffee was 75 degrees in a 70 degree room? It's not going to be cooling near as fast, right? So this describes that situation pretty simply, that's what's happening. But what it doesn't do is tell us how hot the coffee is at any time, right? What we would need to do that is we would need more information. We need the solution to that differential equation, which would be T equals something, something, something with X's or T's in it, little t's, right, for time. And if we knew that solution, which we don't yet, but if we knew that solution, then we could plug in some values and we could find the temperature of the coffee. Okay, one last question. Would K be positive or negative in this situation? Well, you sound like you're guessing. Why negative? Okay, the key, whoops, T prime would be what? No. T prime is not increasing or decreasing. T is decreasing, right? The temperature of the coffee is going down. And that's what T is. So T is decreasing, okay? Which means T prime is, right? Think of the chart. If T is decreasing, T prime has to be negative, right? So the temperature of the coffee is going down. So T prime has to be negative. Now, what about these parentheses here? Why is that positive?
Because the coffee has to be greater.
If it's decreasing, in this scenario, the temperature of the coffee is more than the temperature of the room. So this T is a bigger number than S, so when I subtract those, this is going to be positive. So therefore, if we know this is negative and we know those parentheses are positive, then K has to be negative. What if we would, because somebody in the other class, you guys told me to write T minus S. Somebody in the other class says, well, what if you wrote S minus T? Well, no, the coffee's still changing temperature. The coffee is still higher than the room. But if you wrote S minus T, their question was, would it be wrong? And I said, no, it wouldn't be wrong. But what would be the value of S minus T? It'd be negative, right? Well, in that case, then what would K be? Then K would have to be positive. See, so some people mistakenly think K is negative because the temperature of the coffee is going down. No, T prime is negative because the temperature of the coffee is going down. K is just negative so that it would work out. So it depends which way you have the other. So anyway, just understand, but that's where, again, that chart thing comes in. If you got something that's changing, it's either increasing or decreasing. So its derivative is either positive or negative, and that's where those kind of questions come. Okay, so we want to be able to do something like that. So there's a little bit of new stuff right there added in on differential equation. Okay, can we go to the max min stuff now on sine and cosine 2.7? Okay, and if there's any other questions left on 2.6 that I missed, we can hit those maybe at the end. So let's talk about 39. So this is really critical, this stuff, and we're going to need our calculators here in a second. Not on 39, but when we get to 44. Okay, everybody stand up. Let's go about 45 seconds here. Take a look.
Are you kidding? That is not good for you. That's not good for you. I think we're moving until like 11. Yep.
Happy birthday.
Tim's birthday today?
Tim, that means we don't have to.
And that's your present? You're going to go 16 miles? Nice. All right, here we go. Have a seat. What's it like outside?
It's pretty
Chilly, then windy. I wouldn't know. I didn't get to go out at lunch. All right.
Why was that?
I don't know. I didn't make it out. All right. What's 39? What's 39 say? F, H, G, what was the function? H of X? H of X plus sine X. Okay. So now on one of these problems, right away, look at what it's asking. It asks, where is it decreasing? It asks, where is it concave up? So right away, you know you're going to need H prime and H double prime, right? So, I mean, you could just do those derivatives right away because you know you're going to need them. It asks for, in C, it asks for max and min values. What is that? Is that global or local? In C, 39C, it asks for max or min value. I'm combining two problems.
Oh, good.
Like I said, I didn't get to go out for lunch, so it's kind of thrown me off.
39 is in an ABC.
30, you're right. 39 is the one we got to do everything. 39, local, global, and flex points, all of it. You're right. 44 is the one, okay, well, while I'm saying that, so on 44, they give you this function, they say it's decreasing and inflection points and maximum values, which essentially is all that stuff. Chart, global, everything. So, you can just go through and get all that information, but at some point, as you get better at these, hopefully, you kind of stop along the way and think if there's any possible shortcuts. Now, some people would rather just memorize, okay, do this, do this, do this. And there are kind of some steps in these you do kind of memorize. But, so we're going to start by doing what here? H prime, right? So we're going to do the derivative. And so the derivative of 3 halves x, 3 halves, plus cosine x, derivative of sine b cosine. And we said you should set it equal to 0. Now, quite honestly, on this one you could get away without setting it equal to 0, but most time you're not going to. You're going to think set equal to 0, because I told you that. Do the derivative, set equal to 0, make sure you have the point. However, look at this. Again, it would be nice that when you wrote 3/2 plus cosine x, that for some reason that would make you think of the cosine graph shifted up 1.5. And what would the cosine graph look like if you shifted it up 1.5? So, right? So right away, you would know that h prime is never going to equal 0. There are not going to be any stationary points. And not only that, if h prime is always above the x-axis, think back to chapter 1. That means it's always positive, right? What's that mean if h prime is always positive? H is only increasing. So that means h has got to be doing that. Well, you know, it might be curved, but, well, if h is always increasing, how'd it go? Exciting? Good. Good lunch? I didn't get lunch.
Why not?
I did actually. I got some French fries. I got a very good lunch. So h is always increasing, but what does that do for you if you know h is always increasing? Global max min, I'm thinking of.
Oh.
The endpoints, right? You know the global min has to be at the left edge and the global max has to be at the right edge. So, I mean, you can already do that without even doing a list of candidates. But again, a lot of you will not notice, I mean, you may not notice that. And that's fine. That's fine. We'll still go through the steps, but I just wanted you to see that just in case that comes up again. All right. So, let's go ahead and solve it. So we go ahead and subtract 3/2 from both sides. And we get this. So then you say, okay, where does cosine equal negative 1.5? It's that next group of 3 assignment. Yeah. So when does cosine equal negative 1.5? Well, never. Gee, good luck. So, whoops. So there are no stationary points. There are no stationary points because it doesn't ever equal negative 1/2. Cosine always has to be between negative 1 and 1. Can't ever be negative 1/2. So there are no stationary points. So that means when we go to do our global, we might as well do that right now. When we go to do the global max min, we plug them into where? The original. Our only candidates, whoops, list of candidates. Our only list of candidates is going to be 0 plugged in and 2 pi plugged in. Okay? And so we go back to the original. We do 0 times 3/2 is 0. Sine of 0 is 0. And we plug 2 pi. Sine of 2 pi is 0. 3/2 times 2 pi. 2's cancel. So 3 pi. So that's our max. That's our min. Okay, which we knew was going to happen. We knew the minimum would be at the left edge because of what we talked about a minute ago. And we knew the max would be at the right end, which it is. Okay, so those are our only candidates, so no stationary points. No stationary points also means that there's no local max or mins, right? Because it's never flat. So there can't be any local max mins. There can't be any places where it's increasing, decreasing, any of that stuff. Okay, so now we can go on to inflection points, right? So we need the second derivative. And I think the second derivative is, yeah, same one we had in the problem yesterday, I think, or the other day when we did 37. Negative sine x, where does that equal 0? Well, at, let's see, unit circle, where does sine equal 0? 0, pi, 2 pi. But we said the other day that we do not want to count the endpoints as inflection points. So we also do not count the endpoints as local max mins because we have to look on both sides. Okay, and we don't have that at the endpoint. So pi is going to be our only possible inflection point. So we do a number line for h double prime. Pick some numbers to plug in. Like pi halves and 3 pi halves. Plug those in where? Into the double prime. When you're doing a double prime number line, you plug in the double prime. The prime number line, you plug into h prime. And list of candidates, you always plug into the original. Okay? All right, so pi halves, sine of pi halves, let's see, that's 1 with a negative on it, would be negative 1. 3 pi halves is down here, that'd be negative 1 with a negative on it, would be pi. Now, what's that number line tell us? That's concavity, right? because this is double prime. So this tells us H is concave down, and this is concave up. So it's going from concave down to concave up. So we would have to write that out. X equals pi is an inflection point, and we know that because H double prime changes negative to positive, so H changes from concave down to concave up. All right. Now, finally, we get to number 44, and John will be up again here. Big time. This is a calculator problem. Now, again, like I already said, it tells us that we're looking for decreasing, we're looking for concave up, we're looking for max min values, which means global max min values. So we're going to need lists of candidates, okay, all that stuff. But the difference here is the function. Tell me what it is again. I forgot. 2 cosine x plus sine 2x. All right, and so we're asking about that function f. So we're being asked, well, so we know we're going to need the chart, we're going to need stationary points, we're going to need all that, list of candidates, we need the stationary points, so we're going to need the derivative right off the bat. Now, since you're using your calculator, and so John, go ahead, you can even do the derivative on your calculator if you want to. So John, go and do that. While he's doing that, we'll go ahead and just do it without the calculator. What do you get? So we have to kick out a 2 on that second one. The derivative of sine is cosine. The derivative of cosine is negative sine. And then we got to set that equal to 0. But we just cannot solve that or will not solve that without a calculator. So now when we go look at the calculator, okay, John is doing the derivative here as we speak. Now it's going to write it a little different. That's how I can always tell in a quiz. A lot of times the calculator will put it in a little different form than we would do when we write it. So those of you that have it like that will know you use your calculator, but I don't care. Whatever. Use your calculator to do it if you don't feel confident on it. But it's the same thing we just had. All right. So now what we want to do is we want to set that equal to 0, and we want to solve it. Now remember, I think in this problem we're from 0 to pi. Okay, here's the part that we haven't talked much about that you all need to be able to do. So we go to the calculator and we're going to solve this. So we go to menu and algebra and solve, and then you can just go up and grab that derivative. So that's the advantage of, or it doesn't. It's not advantage because you had to type it in anyway. But so now you type in what you had or that. Oops. Now you got it. Now there's a couple things we got to do here, John. So don't get too big. We're going to go comma x. Oh wait, what did you miss? Equals 0. Comma x. Okay. Now right arrow outside the parentheses, but don't hit enter. Okay. Now if he hits enter right now, here's the thing you got to remember about sine and cosine equations. It goes like this. There's infinite numbers of solutions. Remember the 2 pi n and pi n business? See, that's what you're going to get here if you hit enter. You're going to get this whole bunch of solutions. We only want to look from 0 to pi. So when you're doing these solve problems and you have a fixed domain that you're looking, you want to put that into your solve equation. I need everybody to be able to do this by Monday, so I'm not going to be helping you with this. So you go outside of the parentheses, and do you remember what we do here? I've shown you this before. It's a vertical bar. It's right by the equal sign, control equals. And it's that vertical bar. It's the one some of you thought was absolute value, and it's not absolute value. Okay, now that vertical bar has to be outside of everything. Clear outside all the parentheses on the solve. Now what we're going to do, nope, not a comma, not a comma. And now what we're going to, we can't do that. Yeah, we've got to do 0 less than or equal to x less than or equal to pi, like that. So we go back to that same screen. But the vertical bar means with or such that. So we're saying, hey, we want to solve this with these restrictions. Okay? And you don't need a vertical bar at the end. It's not like absolute value. So you don't put a vertical bar at the end. So you put a vertical bar, you say, hey, okay, with, and then these restrictions, and now you go ahead and hit enter, although I would hit control enter probably. Decimals, since we're using calculator, decimals are pretty good, but Go up and grab it again and don't even hit control enter and see if it gives decimals anyway. Probably gives decimals anyway. Yeah, it gives decimals either way. Okay? All right. So there we go. Now, if it were me doing this, you only need 3 decimal places, but remember when we do our list of candidates, we take these numbers and we plug them back into the original function, and you probably learned in science class, if you take rounded values and use them later, your final answer might not be right. So what we want to do here, I usually write down about 5 or 6 of them. So when I go back to my paper here, I'm going to put x equals 0.523, what is it, 23598, and 2 point, that's fine. Once I get out there, I don't really care how close I am there, 8 or 9 is fine. Okay? Even though you have to put 3 decimal places, you do not have, you could put more. I mean, you could just have that, right? And I think part A asks for that, right? Are there any stationary points? What are they? And this could be your answer right here. You do not have to round to 3. You have to have 3. More is okay. It's easy to write those down because I'm going to need to plug those in later. All right. And so what do I do next? I could do double prime, but I'm going to go ahead and do the number line. You're right. I could do double prime and then whatever. But I'm going to go ahead and finish this out. So let's do a number line. So I got point. Now, on my number line, I wouldn't put all those decimals because this is just for me. 2.617. So I just need to, okay, I don't care about that on the number line. So there's my stationary points right there. So now, and I'm going to use my calculator here. So I need to pick some numbers on the side. So 0.5 will be fine. Here, 1 would be good. Here, 3 would be good. Right? So I'm going to pick some numbers. And I'm going to plug those into F prime. Now, so we go back to our calculators, and let's see. Here was F prime, right? So now, I want to plug a 0.5 into there. How would I do that on the calculator? I could graph it. I didn't think of that. That takes longer. Grab it. Thank you. Okay. Well, graph it. We could graph it and trace. I mean, but that would take longer. Grab it. Go grab it. Okay, I like that. Then what? There's about 3 ways to do it here. I'll start with the slowest and take you to the fastest. And you decide the one you like best. The slowest would be to go delete the x's and put in 0.5. So go ahead and do that. So she's going to delete the x's, put in 0.5s, hit enter. Now what do we care about that number? She, did I say she? Well, because I'm just talking to Natalia. I thought it was, sorry, John. So he puts in the 0.5, and what do we care about that? That it's positive. And so on our number line, we come in here and we put a positive. Now let's back up here a minute, and just for time, we'll get to the faster ones, and we'll do those. Another way would have done it, go back up and grab it again. Not that one. The other one. Yeah, you're going to have to, hit enter. Hit enter. Or put X's, there you go. Better yet. Okay, so put the X's back in there. Okay, so another way would have been to grab it, and now go out to the end and do the vertical bar again. Now, notice this is not a solve. Somebody in the other class said, don't you need to put solve here? We're not solving an equation, right? We're plugging numbers into an expression. Okay, so there's no solve here, because that would really foul things up. Put the vertical bar, because remember, the vertical bar means width. So we could say width, x equals 0.5 right here. So it will do this expression with x equals 0.5. Okay, do 1. We've already done 0.5. You're right. I got you. So, okay, good. Thanks, John. So he did 0.5. But now, why is that faster? Now when I'm ready to do 1, I can just go grab this and change that 1.5 to a 1 instead of changing all the 0.5s to 1s. So that's a little faster. Now there's a way that's even faster yet. Yes?
Okay, but like with timeline, you know how you're doing like timeline?
Right.
You're just doing that because you're figuring out like where it's positive and negative, correct?
That's right. Because I found where it was 0,
Yeah.
put that on the number line, and now I'm picking numbers in between to see where it's positive or negative. So that's why I'm plugging those in. Right. And that's where we were doing them without a calculator before. Now we're just doing it. It's a more complicated equation, so we're doing the same thing, but with a calculator. Okay, now here's the last one. Now again, this might, if you're, like Brittany was just saying, if you're trying to think, okay, here's what I'm doing, you may not want to get so far into all these different fancy calculator things. If you'd rather just think, hey, I'm plugging in 0.5 and you want to type it in each time, that's no problem. Go ahead and do that. But here's the fastest way to do it. All three of them, we can do all three at once. So we can go vertical bar, x equals, and then to put all three in, we grab on the right parenthesis, see above the right parenthesis, there's a curly brackets. That's what they're called. That allows you to put a list of numbers in, and it'll do all of them at once. So you can go curly brackets, and then you go 0.5, comma 1, comma 3, and that will plug in all three of those and give you all three answers all at once, which is kind of cool. So we get, go ahead and hit enter, and go ahead and hit control enter so it'll give it to us as decimals. So, and then you go up and you might have to scroll. So it looks like we get a positive, then we get a negative, and then we get a positive, right? So those are just some little calculator tricks, you know, and how you do that. But basically the bottom line is we got that. Okay? Yeah, not on this problem. This was a no calculator, or a calculator one all the way. All right. Now, so that answers question B, I think, right? Where is the function decreasing? And so you would just say from 0.523 to 2.617, right? And you don't really need an explanation there. You could say because f prime is negative, but you don't really need it. If they'd ask for local max, is there a local max there?
Yeah.
There's a local max at 0.523. There's a local min at 2.6, right? I mean, all that information is there in that number. Okay, now we need f double prime. Okay, so we'll pick up the pace here a little bit. So now we go back to our calculator, and now we want to do the derivative again. Okay? While he's grabbing that and doing that, what's it going to be? It's going to be the derivative of f prime. Negative 2 cosine. It'll be negative 1. And it will, oops, cosine will turn to sine. It's negative sine 2x. So we have to kick out the 2 again, and the derivative of cosine is negative sine. Okay, and then equals 0. All right? So there we go. And so, whoops, we're missing. Wait, you were supposed to be doing the derivative. Or what'd you do? Did you go up and grab that? Well, wait a minute. Yeah. Well, wait. Okay, time out. Start over. Just hit enter. Just hit enter. Because I want everybody to see this. So grab your derivative template. No, not grab. I'm sorry, that was wrong. Take by the 9. Okay, grab the derivative. Okay, put in your x there. Okay, get into that box. Now scroll up to where you had the derivative. It's up there quite a bit. Keep going. There. Right, no. Down. Right there. So that's the derivative. There you go. So now you're doing the derivative of that derivative. And then you hit enter. Okay. Okay. So there's our second derivative. Now we want to solve. Now we go to the solve. I mean, this is worthwhile just going through the calculator mechanics of it. So if some of you are just kind of watching, hopefully you feel comfortable doing that. I mean, and you'll get to practice that. And I think we're going to do number 43 on today's homework. So you'll get or maybe 45, I think. So you'll get a chance to, hopefully today now, after seeing 44, my hope is you can roll through 45 and you can get all this, right? We won't have to talk about this nearly as much tomorrow. And we can just practice and we can figure out the little things we're not. Okay, now what did he forget? No, he's got equal 0.
0 to
0 to pi. You have to limit it to 0 to pi. Okay, vertical bar, right? That's fine. Go ahead and hit it. You gotta stick a 0 in there. Yeah. And then you always want to hit control. I think when you're using a calculator, I hit control all the time to get decimals. I mean, you're already using the calculator. You might as well use decimal. And then, yeah, and mine on this one, just pi, 0 to pi. Okay, so we only get one solution. That looks like pi halves, isn't it? I'm surprised it didn't give it to us. Is that 1.57? What was it? 08. 08 what? It's 07, 9. That's probably enough. 5's in there. Okay, so that's that. Now, actually, I'm not going to plug that one into anything, right? That's a possible inflection point. That's not a candidate. I don't plug that in there. So that's going to go here. So 1.571 probably. Okay, so like 1, we could put it. Whoops, don't want a hash mark there. Put in a 1. Put in a 2. Going to put those into F double prime. Okay. So back up to here. Let's see. Grab your F double prime up here. This is not fair. You're not even writing this down, right? Is that all right? Slightly, kind of. Okay. So vertical bar, right? This is where we just grabbed this vertical bar. And actually, this is nice because now see. Well, no, you're right. Okay, so x. I was going to grab that, but we don't want to grab that. So x equals 1. If you want to use the curly brackets and put them both in at the same time, you can go. Whoops, you need x. That's fine. Go ahead and put 1, 2. But we have to do x equals the curly brackets because it won't know where to put them. Otherwise, you get a syntax error. So arrow back in front of the curly brackets and put x equals. So we're saying with x equals 1 and 2, and then hit Control Enter. And what do we care about those numbers? So the first one's negative and the second one's positive. So we do have an inflection point because F double prime changes negative to positive. So F changes concave down to concave up. But I think actually did one inflection point. It wanted what? D. I skipped over C. What's D? Max. No, D. Where's the concave up? Hang with me now. We're about done. We're about done. Where's the concave up? No. Don't say that. 1.571 to, yeah, not infinity, to pi. 1.571 to pi. We're fading. I can feel it. Okay? One last thing. That is pi half, right? One last thing. C. Find the max and min values. What's that mean? Global max and min is what that means, okay? Find the max min values means the greatest and littlest value. That's global max min. We need list of candidates, which are stationary points and endpoints, and we plug them where? The original F. So we need F of 0. We need F of pi. We need F of 0.5. This is why I wrote down all those values, or why I wrote all those decimal places, because right now I'm needing them because I got to plug back in here. So I need those. Those are my candidates. Stationary points, I have 2 of them. Endpoints, I have 2 of them. I've got to plug those all back into F, which you can do right back there on the calculator. But you got to go back to the original. You don't have to do it, John. I'm going to stop here so we can have a little time to get started. Okay, so list of candidates, we take our endpoint, 0 and pi, we take our stationary points, which are those 2, and we're going to plug those back into the original to find our greatest and littlest value. And whatever those come out to be, I think this one comes out to be negative, this one comes out to be 2, this one comes out to be negative 2, I think, or something, I don't know. And these values here. Alright, and then the max is one of those, and man, you can check that here in a second, but, I wanna give you a little bit of time to get started, cause right away off the homework, it starts with this idea of initial value problem. And plugging in and finding the C value, and so I wanna make sure we're kinda getting the hang of that as we start. Okay, unless you got some other question you wanna ask me. So, the next group of 3 is our homework for tomorrow. Alright, and so, is there anybody gonna be gone tomorrow? Okay, the next group of 3 is basically the assignment. And there's not anything new, really. Tomorrow's gonna be any other questions, any problems we're having, what do we, I'll videotape whatever we do, whatever we go over, and then quiz on Monday. Okay? So that next group of 3 is your homework. So let's go ahead and get to work.
These are the projects that have been
Okay.
like when to use which equation to find